I'm going to start with solenoid valves, kind of the bread and butter of our industry. Hansen makes a family of valves, you know, the smallest, the HS2, you know, up to the big workhorse, or HS4A solenoid valves, and then we also have a dual solenoid valve. I'll show you how all of them work. So the smallest one, the HS2, is available in a 1/4 inch to 1/2 inch threaded connections, or we can do flange up to 3/4 inch. This valve is a direct acting type of lift on it, so when we energize the coil, it lifts directly off the seat, and the flow is stopped in the direction of flow. That's an arrow on the valve. Most of this stuff for our valves is the same with a lot of stuff I'll talk about. 400 psi is our design pressure for standard ammonia products, and then 600 up for CO2 products. And then we'll usually handle minus 60 degree Fahrenheit up to 240, and then we have some certifications if they're required. So again, this little one starts out, it's direct acting, so just so you get the lay of the land here, the red side is the high pressure side, and then the blue is the low pressure side. So again, we're stopping in the direction of flow. You know, here's the seat here. This is all at high pressure. The spring force plus the pressure over an area causes a force downward to make the actual seating of the valve. Once we energize the coil, it creates that magnetic field, it lifts the plunger up, and then we can have flow across the seat of the valve. Very simple, right? Direct acting, nothing fancy. You get it energized, it makes the electrical field, and you pull the thing open. The HS6 is the next one, a little bit reported it, but we still come in as a flange valve at 1/4 to 3/4 inch sizes. Again, FBT, weld neck, socket weld type of flanges available. And again, it's a direct acting. You know, again, seat opens wide when it's electrically charged, like we saw on the other valve. Same kind of, you know, flow in the direction of the arrow. Same type of working temperatures and pressures. But this one we introduce close coupled strainer on the valves. So they have what we call long bolts through them that close couples the flange, the strainer, the solenoid, and another flange. So these are separate components, because I've had people send me pictures and what's this part right here? No, it doesn't. It's one piece. No, it's all bolted together. But this one we introduced the manual stem on, so we can open the valve manually for pumping out and getting liquid out of it if we're going to do service. So this one has it on the bottom, and again, it doesn't lift the plunger off the seat. It's just a separate port in the valve. So I can open that and lift it off the seat, and this will be open for service and pump out kind of situations. So again, high pressure in the red, blue is lower pressure. Usually, minimum, you need about 2 pounds pressure differential to get these to lift. So it's stopped, right? Spring pressure closes it, plus the force of the high pressure liquid causes it to seal.
Piloted around it, correct?
Say again?
Piloted around it.
No, this is not a pilot, it's direct acting, not this one. This is just a liquid that would, or a gas that would come in here. It would skirt, again, there's some clearance here along the plunger, and it gets up here to the top, and then this is a hollow member where the Teflon sits, and it gets, all this is under this high pressure. Or it's just direct acting. Does that answer your question?
Yeah.
So once we energize the coil, it lifts the magnetic field is generated, it lifts the plunger, and then my main seat to the valve is open, and I can get flow across it. Boom, easy, right? Direct acting, it doesn't get much simpler. The HS8A is a 1/2 inch ported valve, again 3/8 inch flanges to 3/4 inch, and also a welding line is starting to be available in this size, but you know, by far, most of the valves are flanged, these small ones. But here we start a pilot operated operation in the valve. So again, we could make all solenoids direct acting. We just need coils about this big to lift the plunger like this, right? 3 or 4 inch, and we just don't do that. We use a pilot operation, a small port to direct a much bigger port. So we'll see how that pilot operation works to control the on-off function. And again, when we energize it, we create this difference in pressure, and then you know, it works and opens the main port, and I'll show you how it works with the drawings. And then de-energize the spring plus the closing pressure of the high side, and actually puts a tight seal on it. Same type of working temperatures and pressures we had on the other valves, and again, close coupled strainer on it. So here it is, close coupled strainer. The manual stem is still on the bottom on this one, but this one, the manual stem works directly on the seat disc, okay? To lift it, and then we open the port to get your manual to open operation if you're doing pump out or service work on the valve. So 2 things you'll notice. This is the pilot port, right, the small port. And it works to operate the much bigger, larger main port of the valve, okay? So again, high pressure in red, low pressure in low. This is all at high pressure here, right? So again, you can't see it, but there's a hole in this wall of this disc. So the liquid or gas pressure comes in here, fills this chamber up, spring pressure plus this pressure, again, over an area, causes that thing to be forced down. It's up here, it's all in this area, high pressure, but since this is closed, you know, it's all gonna stay seated. Spring pressure plus the high pressure flow keeps it closed. Once we open and energize the port, we energize the coil, this plunger lifts up, then it starts to open this, and it bleeds all this high pressure down to low pressure. So once that happens, there's not this pressure, spring pressure, we have to overcome the spring pressure, but the pressure on this side works on the areas here and forces the disc seat up, and then we get the main port to open. The next slide will show the next series of valves, the HS7. We'll show it a little better because it's a bigger valve. But the important thing to note is, again, we've got to get things right at my pilot operation to make sure my main port opens up, right? So this, again, all the rest of them are all pilot operated type valves. You know, energize, slight pressure across the valve, make it go wide open. We de-energize the spring plus the closing high pressure force, you know, caused by the pressure, closes it up. 400 to 600, minus 60 to 240, all that stuff stays the same. Still, we're providing close coupled strainers. Wrong button. Come on, baby. Doubled it. Patience. There we go. Technical problems. Got to get these buttons right and get it facing the right direction. So high pressure. Again, here we can see the hole in this, in the disc seat. High pressure liquid or gas comes in here, fills that volume up, you know, causes that force down, comes up here, it can't cross the pilot. So all this is at high pressure, all this is at low pressure. But once we energize it, energize the coil, we lift the plunger up, it bleeds all this area, all this volume of gas, you know, liquid pressure down to low side. And then again, my high pressure would work on these areas here to start lifting the seat off the main port. You know, so I got this area and this area overcomes, that pressure overcomes the spring pressure, and then it lifts and then my main seat gets open, right? So pretty simple, right? We got the internals pretty much down. No questions?
And what valves are these? What are they called?
These are the HS7.
Solenoid valves, is that what you call them?
These are all solenoid valves. So we're using a energized coil, and again, it's simply an on or off operation. Energized, the valve is open. De-energized, the valve is closed.
So it's just a tiny little bit of lag between the time you can feel that solenoid.
Yeah,
pop.
but you gotta get this port, they gotta equalize, but it's pretty quick. If it's a real small difference, just like it needs 2 pounds to overcome, 2 to 3 pounds to overcome the spring pressure. If it's right there at 2.5, yeah, be more. In this one, like you saw, the HS7 and the HS8, I mean, there's a bore, and you got walls here, right? So there's more friction in these, and if there's dirt or debris or cold oil, all that can add to more time for it to open up. Come on, work with me. The HS4A is probably our workhorse of the industry. If you're out there, you probably recognize this valve, and it shows it with a closed coupled strainer. Solenoid module is up here for the pilot operation, and the big port is down here. I think I gotta go back one here.
Let me update, change the batteries.
Technical difficulties, but darn it. We make it that in 3/4 to 4-inch sizes in welded type, felt flange type operation like you see here. And then you get to the bigger sizes, 5 and 6 inch, and they're just welded line valves, no flanges. But same type of thing, it's got a directional arrow. The flow is in from the strainer through the main port. And you got it going?
Seems like it's working.
Okay.
We can switch gears and it's
Manual stem, we go from the bottom up to the top now. Interchangeable pilots, you'll see when I start showing the regulators how similar they are, because they are all similar on the inside guts. When energized, upstream pressure is ported through the pilot like the other valves, and then we open the big main port. When de-energized, we take away the pilot pressure to the main piston. You'll see this. And we close the valve, the springs close the valve. Safe working pressures and temperatures are still the same, -60 on the low end, 400 on the high end pressure-wise. And we, again, like you saw in the picture, close coupled strainers. Like that, we saw that picture. So here's what it looks like on the cross section. Flow is this way, directional arrow is cast into the side of the valve. The pilot passageway, the solenoid module like we saw on the other thing, the seat up here, and it ports to a much bigger piston area, which controls the main seat down here, and we'll see how that works in the colored pictures here. Again, red being the high pressure, blue the low pressure. High pressure isn't allowed through this port, so it can't get to the top of the piston. Once we energize the solenoid,
You want to switch gears? You want to switch gears? Would that be?
yeah, I don't know, I still gotta kind of point it that way.
Okay.
Can you just turn it this way maybe? That's
Sure.
the computer screen, so it's like over here maybe? I think it might work better. So once we energize the coil like the other ones, right, we open that pilot port. Once we open the pilot port, we can get whatever fluid, liquid or gas up to the top of the piston. And we start putting pressure on the top of the piston to open the main port. So once we get that flow, we start pushing it down. It opens the main port. See here, we can get flow across the valve. Okay. Any questions on the operation of those valves, right? We're using a small port for the pilot ones to control a much bigger port. You know, putting pressure on either the disc or this, in this case, this piston is connected to what we call a V port. And we're pushing that down to get it to open the main port. And then the direct acting, like we saw, just a straight plunger on top of a seat, and we lift it with a magnetic field.
I got a question.
Go ahead.
Oh, what direction does the manual open stop? What's automatic, what's
Oh, good point. Clockwise in is the manual. Counterclockwise out is the automatic.
on all
On all of our
valves?
valves. Yeah. Thank you. Good reminder. So some application, typical air unit here with high gas defrost. I like to start kind of the direction of flow start with the liquid. Most of our big evaporators and coolers and freezers stuff are liquid overfeed type, so we're overfeeding liquid to keep the surface of the evaporator wetted because we get better heat transfer. We get better heat transfer, we need less coil surface, right? So that's what principally we're doing that for. But we have typically on a liquid inlet line, liquid inlet line, some type of stop valve here, a strainer, a solenoid, a check valve, and another expansion valve, right? So we start feeding liquid into the evaporator coil room. We get this all wetted. We provide a fan on it. It moves air across it. You got convection heat transfer. It boils some of the liquid off. We bring liquid and what vapor is boiling out of the suction line. So that's normal evaporation, right? Once we go into defrost, we typically would turn the evaporator liquid line off, keep the fan going so we can get some of the liquid to boil out. We want most of the liquid out of the coil. And then once that happens, we will close the suction valve and then we'll open the hot gas line. We heat up the pan first so we don't get ice mountains in there, right? Or bridging between the pan and the coil. We want that to be the hottest part of defrost. And once it goes, the hot gas goes through the pan, we go through a check valve, and it starts going into the coil, right? Can't go this way, this is stopped. So we start feeding hot gas in there, and we know, right? We got hot gas, high temperature, high pressure gas, cold room environment, right? We build pressure on this space using a defrost regulator, which is typically set about 70 pounds, which is about what, 48, we said yesterday, about 50, 45, 48 degrees Fahrenheit, and it will regulate. So what we want to happen is we bring in hot gas, we know some of it's going to condense, right, because we're in this cold area, but a lot of it's going to be used to melt ice, which is going to cause it to condense too. So we want to move that liquid and gas out of there so we can keep bringing new hot gas into it, right, because it's got the warm air. If you remember our heat, right, most of that heat that we're getting, is it sensible or latent? Yeah, it's a latent heat, right? We're condensing a liquid, condensing the gas to a liquid, that's latent heat. So once that happens, we want to get that out. See what happens if this doesn't work, right, and we don't get it moved out, we get liquid landing here, and then it doesn't defrost, and we get what we call bridging between the pan and the coil. And that's what we're trying to avoid, because once it bridges to the pan and the coil, the next places it's going to bridge is to your floors and your other product or whatever is underneath it, right? So we're gonna use liquid line solenoid, hot gas solenoid. You could use a gas-powered suction stop valve. You could use a solenoid if it's at a higher temperature typically, and then a regulator for this type of evaporator system. And that's pretty much a bread and butter setup. One point of thinking, once you do come out of defrost, we can provide, if you're using a specific kind of stop check, we want to have an equalizing line around it, because what can happen here is we get liquid and gas coming out here in normal operation, right? Once we shut this off, we bring this coil up to 80, 70 pounds, right? And I'm bringing that back here. Once I, get this defrosted, I gotta go back into refrigeration. Well, if this is at 70 pounds and I pop this valve open, it's like a cannon, right? Because in those lines, if they're not pitched right or anything, you got like a wetted perimeter, what they call, part of that is wet, right? And just like on any lake or ocean, right? You get a gas moving across it fast, what happens? Wave builds, and once that wave builds, man, it's a nice hydraulic shock right down the pipe. So we try to avoid that by equalizing the coil close to the suction pressure, then going wide open. We'll show you, Carol or I will show you a valve that can do that all internally equalized. Yeah, give me a go. This is a hot gas where we're going to use a little different. We got hot gas with the soft gas. So, and
Top feed versus bottom feed.
liquid solenoid top feed coming in, bottom feed suction, and equalizing defrost regulator here. And again, this one we're going to use a soft gas. So the build pressure on the coil, we'll start building it with the soft gas, the smaller solenoid. Then we'll go to a wide open, bigger solenoid to really start getting the heat to the unit. Okay, I think we go on that one. Okay, this is a little different one because it's got a gas powered suction stop valve. So again, same kind of liquid feed for the evaporation. This valve is normally open. Once we go into defrost, we turn that off. We let the fans run, pump out a lot of liquid or let it boil off. Then we're ready to close this valve. This valve uses a pilot solenoid, and hot gas comes and closes this valve because there's a piston up there and it seats it. We'll show you the internals of that coming up. And then we start bringing in soft gas and hot gas to the unit to get the defrost going. Same type of regulator to get the liquid and gas moving out of the coil so we don't bridge. And then we come out of it, the hot gas, we turn it off, right? We equalize again to get the coil back down to lower pressure. We can turn the fan on and maybe start building some frost on it. Depending on the flame velocity, you get too high a velocity. If it's coming right out of defrost, you can spray water out of it. Or a lot of times they'll want to build a little frost on it, then turn the fans on if you're low temperature. And then you can go wide open with the gas-powered suction stop valve once it's equalized. Okay, any questions on the application stuff? Seen them all. This one's a little different in that it uses a defrost condensate drainer rather than that regulator going up here. It's pretty efficient if we use all that latent heat, turn it all to liquid, drain that liquid out, and bring it back to suction. Okay. But same type of thing. Bringing hot gas in, liquid recirc normally overfeed for the evaporation. Once we do that, turn it off, hot gas starts coming in. We're going to close that one so we start building pressure. The pressure of the gas, it turns back into liquid. The liquid is drained out through the drainer and then back to our recirculating vessel until we're done with defrost. Bring in soft gas. On the start of the defrost, once you get it all done, you're going to equalize, turn off your hot gas, equalize, bring it back down to pressure, and then when it sits down back to pressure, open a gas suction stop valve or solenoid valve, whatever type of stop valve you're using. Okay, Harold. Does anyone use liquid drainers? Most, you guys got drainers?
But it's not for evaporators.
Okay, yeah, some other.
Yeah, it's different application.
Okay. This is our two-step solenoid. We'll show you how that works, but essentially it's got about a 10% opening and then a wide open feature. And again, we call it the HS4D for dual kind of positioning on it. It comes in a 3/4 inch through 4 inch port. We can get it welded, from 3/4 to 4 inch, but we also have the flange versions. It's, like I said, 2-step dual operation. So there's 2 positions for like a soft opening and then a full open. Of course, all our valves are heavy duty, same type of pressures and temperatures. We can close couple of strainer. If you have something in the field where you think you might need this valve, it could drop in the same flange to flange size as a normal solenoid valve. So in the closed operation, again, this blue is the high side now and this is the low side pressure. Blue closed, both solenoids are de-energized, no power to them, so no gas can come to here or liquid, no gas can come to here. Once we decide we want to do it as a soft or partial open, we energize the coil, just like the other pilot operations. We open that port, that pilot port up, and it pours gas or liquid right to the top of this piston, right? So this piston has a hard stop in it, so it pushes to that point and it goes only partially open. So there's 2 positions here. There's piston, the upper piston and a lower piston. Once we energize the full open piston, that port is open, right? We get gas or liquid ported to the top of this piston. It separates and it pulls or pushes the piston and V-port wide open. So we get a wide open flow. So probably the biggest application for this one is, we can use them on liquid lines, but typically when you have real cold coolers, freezers, you usually try to go with the hot gas 2-step. So you'll bring this thing slightly up to pressure. Because again, if you got high pressure gas here, whatever, 150, 110 pounds, and it could be kind of warm, right? It's coming off your condensers. You don't want to shock your coil, and if it's at -40, I mean it's pretty good. So we use the soft feature to bring this up to pressure and temperature slowly, and then we go wide open and we start really giving it the heat. But you could use them in other applications. You could use it if you like to do again, when you're coming out of a defrost cycle, you could go, like I said, you want to build frost on the coil, and you might want to do start your liquid overfield on a soft setting, so again, you don't rush things into the coil. Slow is good in big industrial refrigeration, right? Do fast stuff happens to you, unfortunately. So we bring in liquid slowly, we start building some ice on the coil, and then we can go wide open and start our whole evaporation cycle. So service of these valves, again, like Harold said, the manual stem, either if it's top or bottom, you turn it clockwise, you're always in the manual position. You're manually opening it. You turn it out counterclockwise, you are in the automatic. So the valve will operate the way it should operate. Energize a coil, it's open on a solenoid, de-energize, it's standing closed. If you don't have the manual stem, all the way out, it can hang up and you'll get some partial flow through the valve. So if you got leaky valves, I mean, if someone's been doing service or something, that's the first thing you want to check to make sure the manual stem's in the right position. And then on the solenoid pilots, we sell these as kits. You wouldn't just for say, I need a new tube or plunger, and I'll show you those parts. You buy them together and you replace them all. They work together. You saw how the plunger slides up and down the tube. They both wear together, so you replace them both, and that's the way we sell them together. Causes of failures. This is the partial list, right? Debris embedded in the main valve Teflon V-port seat. So we've got Teflon sealing here on the white. And if you embed material in there, it's not going to work. It couldn't be, right? You get a big chip across it or something, and it doesn't work. I told a story yesterday, I'll tell it today because I like this story. I went to a customer and he said, all your valves are leaking. Well, how many you got? 40, 50 up on the roof, they're all leaking. I said, well, I'll be over. When do you want me over next week? We'll go take a look at it. So I get over there and it's in Michigan and so well, let's take a valve open, right? So we pump out the liquid and we open up this part, right, the 4 valves, and we look at this piston on top of the piston, and there's just black goo all over. I'm like, that's not how we provide it from the factory. That's not our material. You know, look at it and you're like, oh, yeah, probably right, it's not yours, right? So, well, let's pull that out. We pulled it out, and we pull this V-port out, we pull the piston out, we pull the V-port out, and the V-port has got little tiny pieces of grit just impacted all over it. So this is like, it's not white anymore, it's just like gray. And all those little ridges and valleys, it acted like a metal seat and had all these pathways through it, and it leaked all the time. And about that time, a guy from the maintenance department comes up to me, he's like, I got a whole coffee can full of that black stuff down in my office, man. You come out and look, and I'm like, really? No, he says, I may clean that stuff out of strainers for weeks. You know, I was like, well, okay, now we know what the problem is. And we said, well, let's see what it is. Is it dirt? You know, you got dirty pipe, or is it magnetic? Well, let's take a look at this stuff. So he had it all dried in a pot, and they had a magnet, so well, let's stick a magnet in it. Or we took a piece of paper. You know, like you're in grade school, you put a magnet in, you have the filings on it. It makes those really nice patterns there, north-south and stuff. That's what it looked like. I was like, oh, it's magnetic dirt. Pipe probably has some stuff in it. And I was like, contractor admits to me, said we bought that pipe from like Czechoslovakia or something in 40-foot lengths to save money, right? But it wasn't clean, so they devised a whole little liquid filtration system to knock out all that stuff. But if you had the resources and you didn't want to buy all these, you could. And this is simply a 45-degree angle, and they chose to try to machine some of these. They'll take a little Teflon off and have them recede perfectly again, rather than buying all new pistons. But that's my little sidebar story. Debris on the solenoid mount, modular passages, right? All these little passages that go up in here. Again, if there's cardboard or wood chips or whatever you got laying around, dust, whatever, and it gets those plugged, all bets are off. You're not going to communicate the pressure you need up to the top of the piston, and it's not going to open. Debris packed under the Teflon piston seal ring. So we have what I call a lip seal or cup seal. And, it's up like this. It's got a spring backing in it, and its shoulders. We got a picture of it coming up. Its shoulders, it makes a seal, and it can wipe away grime. But it also, when it comes up, it can also get some stuff packed in there. And if it's not sealing right, it can cause bypassing around there, and then you won't get it fully. It might go partially, but it might not go fully open. So all bets are off on that. And then I've seen them somehow, probably liquid slug, they actually curled around and folded. I've seen them there where they're cut, some debris came through it and cut them. And again, once that happens, you lose that seal around the piston there. You're not going to get full movement of your piston. And then if you have liquid slugs, right, high pressure liquid comes in here, brake springs, the pistons open, you hit the V-port, bend the pistons, all that kind of stuff. All bets are off. So your solenoid's working. One of those guys with 10 plus years. What are you going to check first? Not all at once. Come on. What are you going to check first, right?
Yeah, power.
Yeah, power. You're going to see if the coil's working, right? Right? Coil's working. What's kind of the next thing? And I crank that stem in and out, right? Give it a crank in, see if there's any debris or crap holding it up, right? You got energy, you got, hopefully it freed up, it's moving manually, the spring's moving it up and down, and you're moving it manually down, right? Then if, you try to power it up and it's still not working, then what's next, right? Then it's damn, right? It's nothing simple, right? Then I gotta get my arms dirty and start pumping stuff out, look inside the valve for those kind of things, right? Is there debris, what's hanging it up, that kind of stuff,
Call
okay?
Hansen at that point, tell them it's a piece of crap valve with this over.
No, what's our number one phone call, Harold?
What's the right part number?
What's the right part number?
You can call us for that.
So in like the bigger valves, we have, well, even in the smaller valves, 3/4 and up in the welded lines, we have a removable seat, because that valve is welded in, we want to be able to remove the seat. And then the bigger valves to 2.5 inch we start, right, is removable.
No, it's really 1.5 inches.
Inch and a half, and up. Yeah, that's right, 1.5 inches. Here it is right here. So we have a tool to remove it, right, because there's 4 pins in here that sit up, and we put this tool over it on a 1/2 inch socket drive, and then we can turn this out. When you look down in the valve to remove the seat, there's 2 places for a bolt, right? So the bolt stops this seat ring from rotating. So a bolt will be in one of those 2 positions, right? So if you want to take that seat ring out, the first thing you do is remove that bolt. And it's got 2 positions so the pins, don't hit it, right? So I can't put the bolt right here, I gotta put it here, right? So pick a point, you take it out and we'll replace it once you put a new seat in it. This is the best method that I found. If you can take the valve out and use a drift pin on it, you can get it to move and it'll come out. This method here is what I call the knuckle racker. If you're gonna try this method, please wear gloves, because it will, you can skin your knuckles, okay? You can come up bloody on that method. But this works pretty good too, an improvised bar. You fit a bar across these pins, get something down in there and get some torque on it, it'll take it out too. This method over this one, I guess, if you don't have the right tool with it. So we provide all kinds of different coil voltages, 150, 230, and 24 volt AC, and then we also have a 24 volt DC coil. Our typical coils are, they're watertight enclosed in the Class F, and they meet these NEMA 3 and 4 ratings, or IP32. Our standard coil is a 1/2 inch with 18 inch leads here to wire it in. We also have a DIN type of connection that's available for this type of connection. And we have a quick disconnect plug, the DIN plug that hooks into the coil.
Really?
Pardon?
Quick disconnect plug, though.
Yeah. And I think we got pictures of them coming up here somewhere. And then we can provide these, what we call a beacon pilot light. So it works with induction, so once we energize it, it's like a transformer, right? We power this up and the field energizes this, and then these little LED lights go on. We can use those in all the AC connection types, DC, it won't work. But, and again, we have some certifications for it. But the important thing to know too is when you're replacing solenoid coils, you can't really see it here, but there's a ring on this nut, on this knob, and then there's a O-ring on the bottom. So the O-ring goes on top of the solenoid tube plunger, and then these fit on top of it. And these make like a watertight seal, so you don't get moisture coming down to this part of the coil where it could rust the solenoid tube, and then you can't get the coil off, and this thing starts getting ugly. So you want to make sure they're kind of down to the snipe, not over tight, so you're bulging the coil or anything, but just tight enough so you're getting a good seal on it.
What do you think about putting Loctite, or not Loctite, but like
Never sees on them?
yeah, never sees and all that
In
stuff.
here, I've never seen it done.
Oh yeah, the guys we work with, they slobber that stuff all over everything and put it all over the, what goes inside there.
That's
Yeah.
the secret sauce of refrigeration.
Works pretty good. They come right off, generally.
My wife loves cleaning that out of my clothes.
Oh yeah, it's good stuff.
I think the thing you want to watch out for with never sees is there's 2 different binding agents with never sees. I think one's aluminum based, one's copper based.
Right.
I think the copper based will actually attack neoprene, so you have to be really careful when you're using it on like stems, like
Right.
manual opening stems and shut-off valve stems, because you can draw that into the O-rings and that'll damage the seal.
Right. Can't use the copper seal, right?
Yeah. I think that's okay. I think it's okay.
Silver atoms.
And then we also use, at the factory for the O-rings, we always use Dow 33, which is a low temperature grease, which is always readily available as well.
What do you lubricate your stems with?
Dow 33, which is a low temperature grease that we use. That we don't, we actually, when we were assembling the valves, we actually coat the O-rings in that as well.
Del 33, write it down. Never sees no.
But
It's
you
not-
can
not-
use
no,
it.
you can use it, just
Right.
not the copper.
Is that DOW?
Yeah,
Dow?
yeah, like
Yeah,
Dow
Dow
chemical,
chemical.
yeah.
Okay, oh, gotcha, yeah.
So you just, like I said, when you change a coil, you just wanna make sure, or you take one on and off for servicing, you just wanna make sure, you don't lose the O-ring and you get that seal component set up right so you don't have water migrating into the tube and rusting, and then it's kinda hard to pull it off the next time. Go ahead. Go ahead.
Go ahead.